A galaxy is a vast and enormous collection of stars and dust orbiting a common center of mass. Galaxies come in a variety of shapes and sizes, made up of a few billion to hundreds of billions of stars. The understanding of any large group of objects starts with classification. Most galaxies fall into three major categories.
You've got a galaxy like the Milky Way, which is what's called a spiral galaxy or a disk galaxy, where you've got a central hub, a ball, surrounded by a disk of stars and gas and dust in a spiral pattern. An elliptical galaxy is pretty much what you expect. It's sort of a football-shaped galaxy. It can be a football shape or it can be a ball. These tend to be bigger galaxies. They can have as many as 1 trillion stars in them. These can be pretty big monsters. Irregular galaxies tend to be small and sort of shapeless, like the large and small Magellanic Clouds. These are satellite galaxies to the Milky Way, and they don't really have a very well-defined shape.
Irregular galaxies tend to be small, almost fragmentary. Large galaxies tend to be exclusively either spiral or elliptical. Besides their obvious differences in shape, elliptical and spiral galaxies differ in the amount of gas and dust each contains. Elliptical galaxies, which lack dust and gas, no longer form stars in any significant amount. Early in the 20th century, before galaxies were understood to be island universes in their own right, American astronomer Vesta Slipher was using a spectrograph to try to determine their chemical content. He got a surprise. Almost all the spectra showed significant redshift. It was shortly thereafter that Hubble made his discovery that galaxies were actually vast collections of stars, like our own Milky Way. Hubble quickly realized that the red shift Slipher had found meant that these galaxies were receding from us. Moreover, he determined that the farther away the galaxy was, the faster was its recession. This correlation became known as Hubble's law, the relationship between the distances to galaxies and their velocities of recession.
So Hubble's law boils down to that very fact, that the further away from us a galaxy is, the faster it's moving. And this turns out to be an incredibly useful thing to study in the universe, because it means that we can simply measure the velocity a galaxy is moving away from us at, and that tells us how far away from us it is.
Measuring distance is critical to astronomers. They need to have accurate distances to galaxies to calculate the energy outputs of those galaxies. By knowing the energy output, astronomers can create models of the activity taking place in a given galaxy. But measuring the distance to very distant galaxies is more difficult because Cepheid variables in those far-off galaxies are too faint to detect. Other brighter objects must be used.
So a limitation of using Cepheids to measure distances is that although these stars are bright, they're amongst the brightest stars that you see in galaxies. They're so-called supergiant stars. There's simply a limit to how far you can actually detect them against the background of the galaxy that you're looking for them. The distances to Cepheids we measure in megaparsecs, the unit that we use. So 1 million parsecs, where 1 parsec is 3.26 light years. So we measure the distances to Cepheids accurately out to about 60 or 70 megaparsecs. And to go further out into the universe, it's necessary to use other objects that are brighter than the Cepheids themselves.
These different objects used to measure distances are called distance indicators. Each distance indicator is first calibrated by observing the object in a nearby galaxy with an accurately known distance using Cepheid variables. One set of distance indicators that astronomers use are planetary nebulae, the glowing gases expelled by dying stars. look-back time is a kind of time machine for astronomers. By definition, light takes a year to travel 1 light year through space. So if an object is, say, 1 million light years away, we see it now as it was a million years ago when that light was emitted. The more distant the object is, the farther back in time we are looking.
Light travels very fast, 186,000 miles a second around the Earth, 8 times at the equator in a second. But it's finite. And so one must always remember that when one is looking out into space, one is looking back into time. This is wonderfully convenient if you want to write the history of the universe, because you don't have to speculate on what went on in past times like you do in writing human history. You can actually see what was going on in past times. When I look to the center of our Milky Way, I see it as it was 25,000 years ago, because it's taken the light 25,000 years to get to me. When I look out to the Andromeda Galaxy, the nearest large galaxy to our own, I see it as it was 2 million years ago. Well, 2 million years in a 10 billion year lifetime of the galaxy doesn't make it look terribly different, but I am seeing it at a different time. However, as I start going farther and farther into space, I'm going farther and farther back into time. And as a consequence, I'm beginning to see the universe when it was significantly younger than it is today.
The key to understanding galaxy shapes and ultimately their evolution came surprisingly not through the study of spirals, ellipticals, and irregulars, but through another type of galaxy which defied classification. They showed that environment plays an important role as well.
The fourth kind is called peculiar. Now these are also sort of irregular, but there's a pattern to them. For example, there are galaxies which look like giant hula hoops in space, or galaxies that have collided and are sending out giant streams of stars and gas and dust. They're still oddly shaped, but there's a pattern to them, so they're not really irregular, and those are called peculiar.
So back in the 60s, when people first tried to understand the evolution of galaxies, it was thought that that the interaction of galaxies wasn't the most important thing to how a galaxy formed. It was felt that different galaxies just formed in different ways. And now we believe that galaxies look the way they do now because of what has happened to them in the meantime. We think that mergers, the collisions between galaxies, help turn what were initially spiral galaxies into elliptical galaxies. And they help these elliptical galaxies grow into larger and larger structures, into larger and larger galaxies. So now there's an understanding that the evolution of galaxies depends upon what kinds of interactions they've been involved with throughout their history.
So galaxies aren't really islands in space after all. They often collide or merge, temporarily taking on a peculiar appearance in the process. These mergers have taken place because galaxies tend to form in groups or clusters, encouraging gravitational interaction. Astronomers refer to these huge energy sources as active galactic nuclei, or AGN.
So an active galactic nucleus basically is the central region of a galaxy, and it's really defined as being a very bright center, a very active center. There's a lot of energy coming out of this very compact region in the center of the galaxy.
We've discussed an accretion disk in the plane of the supermassive black hole. But in the inner parts of that accretion disk, what happens is that something forces particles and energy out the two poles, and this is called the double exhaust model. There's two oppositely directed jets of material. This material forms the radio jets and eventually the double lobe radio source when the radio jets decay. It's also where a lot of the high energy radiation comes from, the gamma rays and the X-rays.
Understanding what drives active galaxies and the angles of observation clarified for astronomers why they sometimes detected only one jet in some radio galaxies and two in others.
Now, the double exhaust model, because the particles that form the jets are highly relativistic, going very close to the speed of light, there's an interesting general relativistic effect. If you're viewing the object from the side, so the double exhaust is coming out to either side, you basically don't see the jets at all. You just see the double lobes. The reason is that the relativistic particles emit their light along the direction of the jet, so they're not emitting light towards you. Now, as you change your point of view towards looking more down the jet, you start to see the jet that is pointed towards you because that's where it is radiating its energy along the direction of motion of the jet. But the one on the opposite side is even fainter than it was before because it's sending its radiation away from you. So you're even less likely to see that. Now, it turns out that a lot of single-sided, single-jet radio galaxies were known in the early days, and one of the challenges was to try to see the counterjet. And they integrated for longer to deeper exposures in the radio, and eventually they started seeing these counterjets.
In 1960, two astronomers discovered a strong radio source in the constellation of Virgo. They compared the position of their source to objects in a map of the sky at visible wavelengths, and only found a faint blue star. When a spectrum of this object was taken, there were emission lines, but at wavelengths where no lines had ever been seen before. The object didn't appear to be either a star or a normal galaxy. The breakthrough came when Dutch astronomer Martin Schmidt realized the lines were normal hydrogen lines, but hugely redshifted. Soon, more objects like this were found, and astronomers dubbed them quasars, for quasi-stellar radio sources.
Quasars were noticed as objects that appeared to be stars, but their light spectra showed enormous redshifts, so we knew they were not within our own galaxy.
These redshifts indicated that quasars were tremendously far away, which, coupled with their apparent brightness, meant that they were incredibly luminous, far more powerful than a normal galaxy. This stunned astronomers.
Maybe the redshift is wrong, maybe it's in our galaxy, maybe it's not. Well, eventually, people came to pretty much agree that all these objects are outside our own galaxy, very, very far away. The redshifts that we see are truly cosmological, truly large distances.
In the 1950s, radio astronomers doing maps of the sky found a class of objects. They weren't sure exactly what they were at first, but often they appeared to be doubles, as if they came in pairs. Not always. Some of them were single. And in the 50s, they found that those were associated with galaxies as well, but they didn't really know how they related to Seyfert's galaxies. So that they were basically just called radio galaxies.
A radio galaxy is a galaxy that not only emits visible light like that you see with your eyes, but it also emits radio waves.
At low-energy radio wavelengths, radio galaxies look very different than how they appear in visible light. What astronomers see in these different wavelengths helps them understand not only the physical processes in these galaxies, but also what's going on in different regions of these galaxies.
At the longest wavelengths, the lowest energies, radio waves, they typically don't see what we normally think of as in galaxy pictures. They don't see the starlight, and they don't see a lot of what we normally associate with pictures of the Milky Way or the Andromeda Galaxy. What they see instead typically are these big radial lobes that are outside the boundary. In the early 40s, Carl Seifert, working at Mount Wilson Observatory, discovered that some galaxies had very bright centers, and that these centers showed interesting spectral signatures. They showed very strong emission lines, and sometimes very broad emission lines, which aren't seen in other galaxies.
A spectrum from a normal galaxy will be a composite of the spectra of all of the stars within it. That is a continuous spectrum with dark absorption lines. Seifert galaxies display these normal absorption lines, but also show broad emission lines coming from the galaxy's cores. Emission lines in a spectrum indicate the presence of hot, low-density gas. The fact that the lines are broad indicates the gas is in rapid rotation. Gas that is moving toward us during the course of this rotation emits lines that we see as blue-shifted, while the gas that is moving away from us gives rise to red-shifted lines. This red and blue shifting of the gas blurs the spectral lines together, broadening them. Astronomers found that the only object capable of generating that much energy is a black hole. It is possible for black holes to generate light, and lots of it. But that light doesn't come from the black hole itself. It comes from the material falling into it. But the sheer amount of energy emitted from quasars implies that the black holes powering them must be incredibly big, incredibly massive, billions of times the sun's mass.
That somehow when a galaxy formed, material was accumulated in great amounts, high densities, in the centers of galaxies. And the material is gravitationally bound, kept accreting until you wind up having so much gravity in one place that the gravity actually overcomes the ability of light to escape. Then you get a black hole. Well, there's no really upper limit to how much material you can keep accreting in there. So what we're talking about is something that is maybe hundreds of thousands to 1,000,000 or more times the mass of the sun, all located at the very center of a galaxy and taking up space that is of the order of solar systems in size.
Black hole itself doesn't actually produce that much energy, but it's the gravitational pull of the black hole that is converted into energy that we can see. And how it does this is that the gas and dust surrounding the black hole
coming down, caught in that gravitational field, orbiting and gradually spiraling in toward where that supermassive black hole is, the material is just atoms, and these atoms start colliding and crashing into each other because they're being put down, they're funneling down into this high density region. And atoms are just whacking each other every place, and as they whack each other, they knock their electrons off, they strip their electrons off. Occasionally an electron will find another atom and recombine with it, and it lets off electromagnetic radiation.